Start the recording. Okay. I'll mute everybody just to march through. Okay. Uh, Basically, we start off with the system of chemical communication known as the endocrine system. And by definition, endocrinology is the study of the hormones or the chemicals that allow communication within the body. So our growth, our metabolism, sexual characteristics, even personality, all derive from the endocrine system. Again, communication within the body. We know of two systems. We last left off with the nervous system, where there is rapid communication from one nerve cell to another to allow for messages to transmit throughout the body. And now we're looking at a much slower system of communication. Let's compare the nervous and the endocrine system. Because we last left off with the nervous system, remember the dollar bill drop? We kind of discussed the fact that nerves move very fast in terms of their impulse or message transmission, but that their effects is short lasting. You know, you catch the dollar bill or you don't catch the dollar bill. It's an electrical transmission. It doesn't last long. The endocrine system is very different. For the hormones to diffuse from what we call endocrine glands produce endocrine hormones. For those to diffuse out, go through the bloodstream, get to their target organ, it takes some time. So we say that the endocrine system is therefore slow acting. Slow to get a reaction. And it is long lasting. It acts for a long time. And I know this sounds a little bit confusing, but its effects last for a long time. If you, for example, eat a donut and your sugar level goes down after insulin is released, then it doesn't just spike up and spike down within milliseconds like a nerve does. It takes some time to adjust. So chemical transmission is long lasting, slow acting, whereas the nervous system is fast, but ends quickly. Let's go over what happens with hormones. Okay, let's move on to the hormone. A hormone is a chemical messenger or a chemical signal. So just make sure you memorize that. Hormone means chemical signal. There's a lot of different types of hormones. There are, insulin and glucagon that we talked about in ANP1 that regulate sugar levels. There's human growth hormone. There's thyroid stimulating hormone. There's ACTH. There's TSH. In other words, it's an alphabet soup of different types of hormones. And that list is in figure 14.38, okay? Page 552 and 553, figure 14.38. If you take a look, it's an alphabet soup of different types of hormones that cause different actions in the body, right? And there's a chart showing you all the different types, as well as a picture on page 552 of all the glands that produce the hormones, all right? The chemical signal, let me just define a hormone. Chemical signal transported by the circulatory system causing a response in a specific target cell. All right, what does that mean? The image you see up here is a hormone or a chemical that is having to dock to a receptor on a cell membrane of a target cell. The target cell is the thing that the hormone acts upon. But the hormone basically has to dock to a receptor. It has to have a specific fit. So make believe my hand that's moving is the hormone and the other hand is the receptor. The fit has to be just right. Just like a virus gets into your body using a receptor, hormones get into target cells, which are cells that are going to react to the hormone. They have to attach, the hormone has to attach to the receptor with a specific fit. And if that doesn't happen, the hormone's not getting in. That is what makes a hormone specific. We have about 50 different types of human hormones. I have probably about 20 of them on figure 14.38. So that gives you an idea. And in the end, if you scroll down through all your notes, don't do it right now because I want you to follow along. I have what we call a concept map. So concept map is like a cartoon of ideas, putting all the concepts together so that you can remember it. They say that if you can put all of a chapter on one single page from memory, that's when you really know it well, all right? And interrelate it with arrows. That's a concept map. And I'd like you to do that for A&P2. I have a box at the end of every chapter in the textbook for you to, kind of write. I know it's an ebook, but basically you get the idea that you can put the entire chapter on one page and do a concept map. I have a little sample concept map at the end of this chapter in order to help you get an example on how to do that. But to make a long story short, even though there's 50 types of hormones, there's really 3 ways in which a hormone gets into a target cell. Let's start with letter B, all right? Steroids. Steroids are fat-based, if you remember from ANP1, fat-based. They are hydrophobic. In other words, they're afraid of water. And they move directly through a cell membrane. Remember that a cell membrane is made up of a lipid bilayer, and like dissolves like. So the lipids will generally go directly into a cell membrane and not have to dock with a receptor protein. I just want to say that that's a great way to get into a cell. You don't have to mess around with enzymes, receptors, all kinds of stuff. So steroid hormones, such as the sex hormones, also known as gonadal, and the adrenocortical hormones, both of those are lipid-based and go right into the cell membrane. So you can remember this very easily. If I ask you on a test, how do steroid-based hormones get into a cell? You can just say directly. That's nice, right? The other hand, we've got amino acid-based hormones. That means protein, if you remember from ANP1. Protein hormones require you, if you're a hormone, require you to dock to a receptor in order to get in. So, for example, thyroxine and epinephrine. Thyroxine is the metabolism hormone. Epinephrine is kind of the energy surge hormone. Both of those need a receptor to get in. We're going to talk about the way in which peptide or amino acid hormones get into a cell shortly. But they take a little more doing. Eicosanoids are active lipids. They are a special type of lipid or steroid hormone, such as prostaglandins, and they also go directly through a cell membrane into a target cell. Prostaglandins are an interesting type of hormone. I want you to think about prostaglandins. It starts with the letter P, and pain starts with the letter P. Prostaglandins cause pain. I hate prostaglandins. Tylenol, when you take it, reduces your prostaglandins. That's a good thing to remember because everyone in the hospital likes Tylenol, all right? And Tylenol reduces prostaglandins so you don't feel the pain as much. And it's kind of an interesting point. Prostaglandins increase during childbirth, causing uterine contractions. And it increases your blood pressure, increases blood clotting. It's kind of interesting. Prostaglandin levels go down during pregnancy. All right, so less pain is felt by the pregnant mother, except when the poor pregnant mother needs it most. Prostaglandins then go way up during pregnancy. During childbirth. So again, let me repeat. Prostaglandins are lower for a pregnant woman and then increase during childbirth. You would think that nature would let you feel less pain, right? When you're putting a large creature through the cervical os. However, nature's cruel. It wants you to suffer and therefore push that baby out. And so prostaglandins go up to make the whole thing a lot crazier and more painful. Now, I don't want to frighten anyone. I was in all 3 of my kids' childbirths, in the hospital. And I'll tell you one thing, the C-section was the easiest. I'll tell you that, because the natural childbirthing was tough. But anyway, I don't want to freak anyone out. I did not faint. I was yelled at by my wife. I don't know if I recommend being in the room. Okay, moving along. But on an important note, hormones do a lot. And actually, during the childbirth, they got rid of my wife's nausea, pain very quickly with chemicals. So chemicals do a lot in the body. And that's really what this lecture is about. The alphabet soup of all the different types of chemicals known as hormones that affect the body. And hormones often act in opposition to each other. And I just want to reintroduce you to the sugar regulation. You got to have about 90 milligrams per milliliter of sugar in your blood. And it's got to be pretty steady. It doesn't have to be that exact number. You know, you have a little sugary coffee, it goes up, no problem. But it can't go up too much, can't go down too much. 70s to 120s, 30s is your norm in terms of numbers. So there's always a range. But to make a long story short, hormones often act in opposition to each other to accomplish negative feedback, right? As one thing goes up, the other goes down. So insulin and glucagon you've been introduced to in ANP1. Insulin decreasing blood sugar and glucagon increasing blood sugar. And we've gone over that process. As you know, negative feedback is a reversal of the original stimulus. So often it's the hormones that act in opposition to keep us in homeostasis, all right? Another thing I wanted to mention, this is just as an aside, I don't want to go crazy about this concept, but pheromones. Pheromones are chemicals that communicate in between two different organisms, two different animals. So we believe that some of our sexual drive for each other is a result of chemical communication between two different creatures, not within. And that's a pheromone. Ants conduct war, alarm calls, food recruitment, and they detect in such low concentrations these pheromones that they have a whole life based on pheromones. I don't want to go crazy about ants. The cover of your book has an ant. It's interesting because they sense things very different than us, but this class is clearly not about ants. But I think you should appreciate sometimes philosophically your own biology by comparing it to a whole world of other creatures around us. So, but let's now go over the general mechanism of hormone interaction. All right. How does a hormone get into a cell? Well, step one, there's target cell specificity, a specific fit between the hormone and the receptor. And that specific fit depends on, number one, obviously the affinity. The word affinity means, it's a good college word, love for or connection with. The binding or affinity or attraction, that's a better word. Affinity means attraction. The affinity or attraction between a receptor and a hormone, all right? How well that fit happens, that's one thing. It also, the specificity, in other words, how well a hormone attaches to a receptor depends on the number of receptors you have and the amount of blood hormones you have, right? So if you don't have, let's do an example, if you don't have enough insulin in your body, your pancreas is not making enough insulin, it's not going to be an effective hormone, right? If you don't have enough receptors for insulin, it's not going to be an effective hormone. Or if that affinity, that shape somehow does not allow for a connecting of the receptor and the hormone, that too will affect target cell specificity. And so what does a hormone do when it enters a target cell? A hormone alters a target cell's activity. It does something to it. And we don't have to get specific about each thing, but in general, it either increases or decreases an enzyme's activity. It may change mitosis, right? It may change how much that target cell grows, like in the case of human growth hormone. It may change a membrane's permeability, how much sodium can come in. Very often that's how your blood pressure hormones work. Aldosterone, antidiuretic hormone. And I'm throwing out a lot of words. You may have seen these before, but we're going to go over them in detail. It may increase the synthesis of proteins. That's a very common one. Proteins, in other words, products to secrete. You may have a hormone going to your thyroid, known as thyroid stimulating hormone, causing the thyroid to secrete thyroxine, which controls your metabolism. If you've gotten to this week's labs, your experiment with the little rat addresses the production of thyroxine and the control of metabolism based on that. Now, when we look at how receptors and hormones interact, we look at two terms, upregulation and downregulation. Let's take diabetes type 2. That's, it used to be called adult onset diabetes. Now it's called diabetes type 2 because some kids get it, when a person, this is a very big oversimplification of it, but downregulation occurs when there's prolonged exposures to hormones and they desensitize the target cells. And in regular people language, that says downregulation equals, you can write this down, wearing down of the receptors. If you use something too much, if I use my shoulder too much, it hurts in the morning. Use your neck too much, you're going to get arthritis. Too much overuse causes damage in cells. You got to know about that in anatomy. It's the wear and tear hypothesis of how anatomical structures basically get worn out due to age and overuse. Now, if you're eating a lot of ho-hos, sugar, all right, you're going to eventually wear down the receptors between the insulin, right, and the insulin receptor. And that's the idea behind the development of type 2 diabetes, that you prolong exposure to the hormones because you have induced so many sugar highs, let's say, through the ho-hos or whatever you're eating, that you kind of wearing down the sensitivity of the insulin receptor to the insulin. So that's downregulation. I like that one. Well, it's a big cause of the obesity epidemic, and the obesity epidemic is a big cause of or linked to the diabetes epidemic in the country. And that intrinsically links to who, COVID-19, because that is a risk factor for developing bad symptoms for the COVID. So I have to tell, for the coronavirus, I have to tell you that all of this is related, and it's related partially to diet. And I don't want to get ahead of myself, but because we're going to do digestion and nutrition much later in about 3 weeks. But it's a great piece, really. Chapter 12, I believe, is the nutrition and digestion unit. If you want to look over it in your spare time, it is a great chapter that I've written on synthesizing the many problems of nutrition in society. Okay. And one big issue is the development of diabetes. All right, that's downregulation. That's a long-winded answer to what downregulation is, which is a lot of exposure to hormones desensitizes target cells. Upregulation is a little more uplifting. Basically, target cells make more receptors in response to increased hormone levels. What does that mean? Let's use an example. Estrogen causes uterine receptors to uptake progesterone. As there's more estrogen, there's more uterine receptors developed by your cells to take up more progesterone. Upregulation causes more receptors to be formed in the presence of hormone levels. All right, that's a weird thought, but reproductive hormones often work like that. So why don't we just break down the hormone interactions into 3 different interactions, okay? Number 1, we just went over antagonism. If you're antagonistic with someone like I am with my sister-in-laws, you're arguing. Do you know what I mean? One hormone opposes the action of another. There's an argument. In other words, as one causes things to go up, the other causes things to go down. Now, insulin and glucagon are our prime examples because you've been through it. That's why I'm bringing that up. Sugar goes up. Blood sugar goes up due to glucagon. Blood sugar goes down due to insulin. Maintaining a balance, a homeostasis. Okay, another word is synergism. Synergism, that's a good college word too. Should definitely memorize. Means working well together. Now, you can always say, we work synergistically together. Then you sound real smart. Synergism means one hormone enhances the effect of another. So let's take epinephrine and glucagon. Epinephrine is causes the excitement, the fight or flight response. You have an epinephrine high, you're running, you got to have enough sugar, right? So glucagon provides that sugar. It causes the liver to release glucose or sugar so that the epinephrine can work and do what it can in the body. That is synergism. One works with another together. Permissiveness is the final hormone interaction, and that occurs when one hormone requires another to be present. So, for example, thyroxine allows for human growth hormone to work or reproductive hormones to work. If you don't have the metabolism behind reproduction, you're not going to develop reproductive structures. So you've got to have enough thyroxine. You're not going to grow without thyroxine. Cretinism, Cretinism, well, I may as well put that in the chat room. Cretinism, just you don't have to know that right now. Cretinism is a form of dwarfism caused by a lack of thyroxine. The individual has enough human growth hormone, so they would grow normally, but they're hypothyroid. In other words, they don't make enough thyroxine for normal growth. So that's a point. Okay, moving along. Again, I'm just telling you and helping you remember, steroid hormones pass through a cell membrane very easily, enter a nucleus, cause transcription of the genes. If you remember that from general bio, that just means making proteins that a hormone wants you to make. Estrogen, the female sex hormone, progesterone, another female sex hormone, testosterone, include the males, all of them come in, all of them enter a cell just directly. That's the key word, directly. Steroid hormones enter directly into a cell. Peptide or protein-based hormones, also amino acid-based hormones, that all means the same thing. They're charged a little bit, you know, so they cannot pass through a cell membrane. And this is a tough thing to teach, the two different systems of hormone transport. And there is a picture of hormone transport, figure 14.37, page 552 if you want to follow along. If you take a look, the right side picture is the lipophilic or steroid hormone. That means the same thing, the steroid hormone. And that picture on the right shows how a steroid hormone goes in directly. Now the picture on the left shows, whoa, how an amino acid goes in. We call it the CAMP system or the IP3 system. The cyclic AMP system and the IP3, also known inositol triphosphate system. This is kind of a hard topic to teach, one of the hardest in this course. And I think I want to simplify it by saying, you got to get the big picture. This is the way in which a hormone attaches to a receptor if you're a protein hormone and gets into the cell and causes it to react. Both processes do the same thing. They both start off by binding to a receptor. And the receptor, the hormone that binds to the receptor is known as a first-degree messenger on the cell membrane. Right? If you look at the picture on figure 14.37, top left of page 552, you see the hydrophilic, or another word for that is protein hormone, first-degree messenger attaching to the receptor. Then, step 2, it causes an enzyme to change if you look at the picture. Now, which enzyme? If you're a CAMP enzyme, it causes a G protein or secondary messenger in the membrane to be activated using MP3. And then the active G protein causes another chemical known as adenylate cyclase to be activated. And adenylate cyclase, if you look at the picture, makes ATP into cyclic AMP, everyone. And cyclic AMP is the secondary messenger that moves within a cell that causes protein kinases, which are enzymes that cause the response to whatever the hormone wants it to do. All right. You could say it phosphorylates proteins. That means adds phosphates to proteins, does stuff to the target cell. Now, the other type, all right, of membrane transport for an amino acid hormone is known as the IP3 system. and it's named for inositol triphosphate, which you will see is the secondary messenger, IP3, right here. So why don't we go over that? The process starts again with the hormone and receptor binding. And if you look on page 552, same thing. Hormone receptor binds, much like the top process, the G protein is activated, but now there's a change. The membrane protein is not adenylate cyclase. Instead, it's PIP2, phospholinositol diphosphate. You do not have to know that. That is sitting in the membrane. But that's cleaves that phospholipid into the IP3 system, basically an IP3 and a diacylglycerol. The IP3 causes calcium to be released from the endoplasmic reticulum. And the diacylglycerol activates the protein kinases. Both of these just basically change enzyme activity. They get things done, in other words. So if you're not lost now, you're crazy. Let me make this very simple. What you have to know for this is that steroid hormones go directly through a membrane and amino acid-based hormones cannot. They must bind to a receptor and they must go through these different steps. You should know that there's one set of steps called cyclic or CAMP system, and the other one is the IP3 system. Those are the two ways that proteins get into a cell. Protein hormones get into a cell. And you should know that one has a secondary messenger of adenylate cyclase, the other has a messenger of IP3. Okay. You also should note that a G protein is the first thing that both systems activate when the hormone binds. Last but not least, I want you to know who does what. In other words, what hormones are involved in the IP3 system versus the cyclic AMP. If you don't know the answer, say cyclic AMP, all right, CAMP. If you take a look, the IP3 system involves only the neurotransmitters, which you remember from the ANP1, the nerve hormones. It involves growth hormones. It involves ADH and oxytocin. All right, those are the hormones involved in the IP3 system. Now we're about half past our lecture time. At this point, I want to give you an overview of the endocrine organs and their diseases that go with it, and then we'll open up for questions at 10 o'clock. You can always ask a question in the chat room, and I will address it as we go along, okay? But anyway, the endocrine organs. Take a look at page 553. You see a list of all of the endocrine glands and their hormones, all right? It says principal action, that means what it does. Primary target, that means who or what the target organ is. And on the left, it gives you the gland that makes a particular hormone. There's a picture of that on the opposing page. Turn the page to page 554, and that's a picture of the pituitary gland and the hypothalamus. For this particular course, I call the hypothalamus the master gland because it controls everything, right? The hypothalamus is a lower part of the brain, a little tiny section, pea-sized, that receives information from other parts of the brain and from other parts of the body. It has something special known as neurosecretory cells. That means cells that are nerves that secrete or give out hormones. And they release hormones to the pituitary to control the pituitary. If you see, most teachers will say the pituitary is your master gland, but I say it's the hypothalamus because the pituitary obeys orders from the hypothalamus, all right? The pituitary listens to the hypothalamus. And to make a long story short, let's talk about the hypothalamus. Hypothalamus is connected to the posterior or backside pituitary through the hypothalamic hypophyseal tract, as you can see on figure 14.38, top of page 554. Look at that little tract. It's a little, let's just say a little connection, a stalk between the hypothalamus on top and the pituitary on the bottom. Pituitary is like a little sac. And there's a front and back, or an anterior and posterior pituitary, all right? Each doing a different thing. Now, neurosecretory cells, what does that mean? That means it releases hormones to the pituitary when stimulated by nerve cells. It sends out messages, both electric messages through nerves and chemical messages of hormones to stimulate the pituitary. Why don't we talk about the backside of the pituitary, the posterior pituitary? Very simple. It does not make, I repeat, it does not make a single hormone. It stores hormones from the hypothalamus. And what does it store, everyone? ADH and oxytocin, both IP3 mechanism hormones. ADH is known as antidiuretic hormone. It is water conserving. That means it keeps you from peeing. Let's talk a little about antidiuretic hormone. Have you ever heard of breaking the seal? Maybe I shouldn't say this on YouTube. I don't know. Breaking the seal, when you drink, you basically have to go to the bathroom more, right? And breaking the seal means once you go once, you got to keep going. Well, breaking the seal is kind of a myth. You're going to have to keep going no matter what. Because what happens is alcohol is a depressant. Even though it may make you happy, it slows everything down. That's why, you know, the dollar bill drop with drunken people works a lot better and can get you beaten up. But I think to make a long story short, ADH slows down and therefore slows down its water conserving properties. It does not keep conserving the liquid in your kidneys back to your blood. And so you have to pee out more. So that's antidiuretic hormone. Anti means against, diuretic means peeing. Drugs that are diuretics mean that they make you pee. So that's stored in the posterior, P for posterior pituitary. Oxytocin is what's involved in birthing. And remember we talked about that in ANP1, positive feedback. Oxytocin causes uterine contractions and childbirthing. And it's made by the hypothalamus, stored in the posterior pituitary. And again, its mechanism is also the IP3 system. Now, that's the posterior. The anterior pituitary releases something known as tropic hormones. Tropic hormones don't do anything. They except stimulate other glands to release hormones. So the anterior pituitary makes something known as TSH, which stands for thyroid stimulating hormone. And if you get this wrong on the test, you got problems. What does it stimulate? The thyroid. It acts on the thyroid to make thyroxine, which controls your metabolism. So it acts on the thyroid. ACTH, and I told you this is an alphabet soup. There's a lot of abbreviations, in other words, of the different hormones. Adrenocorticotropin stimulates the adrenal cortex to make corticosteroid hormones, all right? Corticosteroid hormones are hormones that control sugar levels, in addition to insulin and glucagon. Gonadotropins stimulate the gonads to develop. LH promotes gamete development, luteinizing hormone, goes to the gonadal tissue to promote ovulation, all right? FSH, again, these are all things that stimulate other glands to make stuff. Follicle stimulating hormone, FSH, develops the gametes. And then finally, we have prolactin, which causes milk production in the breasts. All of this coming from the anterior lobe of the pituitary. Now, growth hormone is also made by the anterior lobe. I put that separately because that is not a tropic hormone. That directly stimulates bones to grow and skeletal muscles to increase in size and divide. And if you remember your epiphyseal plate, you know, between the diaphysis and the epiphysis of the long bones, that closes at night. You tend to grow at night more. And that's when growth happens. Giantism is above 8 feet tall. Dwarfism is below 4 feet tall. All right, that's our general definition. Easy to remember. If you're over 8 feet or below 4 feet, then you're out of the norm. All right, obviously that's, you know, if you're 7 foot, you're pretty tall, and if you're 4'5", you're pretty short. But I'm saying that that's the official definition of giantism versus dwarfism. And that often has to do with growth hormone. And we gave you an example of cretinism before, where it's not so much the growth hormone, but the permissiveness of the thyroxine. So anyway, so that's just some examples. Acromegaly, if you see pictures of acromegaly, I should get you some pictures right here and now for fun. Acromegaly. I spelled it wrong. Oh, the heck. Image. I was like an image. That's when growth hormone remains too much, you know, too much. There's a person, and the hands and feet get big. The cheeks get kind of large, as you can see. I guess here's a picture. Burrow, frow, enlargement of the base of the nose. There's some characteristics when the growth hormones occur too much. I had some better pictures. There's acromegaly in a lady. When the growth hormone continues and the individual has some distorted features. All right, that's acromegaly. You can see in the hands, whoops, my face is in the way. There we go. You can see that an example. All right. Whoops. Put that right here. Okay, moving along. We've talked a lot about the thyroid. Your lab is based on the thyroid, lab number 1. And let's talk about where the thyroid is. If you take a look on page 552 and go like so in your neck, right here at the base of your neck is a butterfly-shaped image that, or a butterfly-shaped gland. It's one of your largest glands, and that's called the thyroid. And the thyroid has little buttons in them, and the buttons are parathyroids. The thyroid makes triiodothyronine and thyroxine, which together work to control metabolism in your body. And here's the physiology of how the thyroid works. The hypothalamus that we just mentioned in the brain sends the message to the anterior pituitary to produce TSH when thyroxine levels are too low. And TSH stimulates the thyroid to make thyroxine, which regulates metabolism in the body. That is its function. More thyroxine means more metabolism. And that thyroxine, if you notice, has an arrow back. That arrow back limits the anterior pituitary. It's negative feedback. As you make too much thyroxine, the anterior pituitary will produce less TSH. So it slows the whole process down. You'll see this very frequently with physiologic mechanisms. Well, anyway, let's go over hyper versus hypothyroidism. You're going to see a lot of cases like this. Hyperthyroidism, the word hyper, you know, means too much. So it means an overactive thyroid. And that that's caused either by too much TSH or overactive thyroid cells themselves. And Graves did, so what happens? Let me say. Hyperthyroidism, usually you're skinny, energetic, you got kind of bulgy eyes. I always had big eyes and was energetic, but never had hyperthyroidism. They were always wrong in their diagnosis, and I knew it anyway. But you never know. Definitely the coffee makes me energetic. Got to have that. But getting back, hyperthyroidism means an overactive thyroid. Those are some symptoms. You might say that's good, but not really, because you kind of wear out the heart, cause more high blood pressure, heart palpitations, and can even lead to the opposite, hypothyroidism, which is an underactive thyroid, where the thyroid is not producing enough thyroxine. So there's weight gain, there's intolerance to cold, there's increased cholesterol, and often a goiter, which is an enlarged part right here, results where the thyroid enlarges because there's not enough thyroid being made. So the cell actually increases the number of cells, not enough cells. So the body increases the number of cells to compensate for the lack of thyroxine and makes a larger thyroid. So goiter is a symptom of hypothyroidism. The thyroid and the parathyroid also control your calcium levels. And I remember the year was 19 God, 89, and I had cell bio. I had one question on the final. This class was unbelievable. And the guy just said, discuss calcium. And you had to write for 4 hours in these little blue books. I don't know if you still have those. I don't use them. But anyway, write a lot of essays. 4 hours on the calcium. Your calcium level is vitally important in your body, from nerve function to hormone function to enzyme function to strong bones and teeth that you've memorized in high school. But there's a lot of things. And so calcium regulation is very important. That's why I'm emphasizing it. And if you take a look at figure 14.39 in the text, right, page 555, take a look quickly. That is the control of calcium that we're going to go over right now. So if you follow along, calcitonin lowers blood calcium. All right, that you got to remember. So if you have too much calcium in the blood, calcitonin made by parafollicular cells of the thyroid, all right, this is under the thyroid. Calcitonin is made by the thyroid to lower blood calcium levels. Of course, it's antagonistic to parathyroid hormone. Who do you think makes the parathyroid hormone? That's correct, parathyroid gland. The parathyroid gland is embedded, as I said, in, here it is, take the picture, embedded in the thyroid, but it's found in your chest, in your neck, and other places. So when they take the thyroid out, some people still have a parathyroid. And the parathyroid gland is involved in lowering raising blood calcium. It's the opposite of calcitonin. It has little chief cells inside that make PTH when there's not enough blood calcium, so it increases blood calcium. So calcium is removed from bone. Osteoclasts break down the calcium. Calcium is absorbed more from the kidneys, as you can see in the image in figure 14.39. And if you look further, calcium is absorbed from your diet, from your small intestines, your intestinal mucosa cells, all increase blood calcium levels. And PTH also activates vitamin D, which activates something known as calcitrol to get more calcium absorbed by your intestines. Calcium, PTH causes increased calcium uptake by the intestines by activating vitamin D and calcitrol. So you know what I mean? We are antagonistic in figure 14.39 to keep a stable amount of calcium in the blood. We say that the adrenal gland, we're moving on now to the adrenal gland. If you turn the page to 558, figure 14.41, there are a series of, again, go to page 558 at the top. There's a series of hormones produced by the adrenal gland. And I want to address the structure of the adrenal gland. It is sitting atop the kidneys. It sits on top, and the bulk of the gland is the adrenal cortex, which is the outside of the gland, and that's under pituitary control, as we just talked about. The inside of the gland is known as the adrenal medulla. And if you note, I'm giving you an overview of all the glands, and then we can go back and discuss the details in the question and answer at the end, okay? But I just want to address the fact that the adrenal cortex makes 3 different hormones or hormone classes. One is mineralocorticoids, which basically suck up water back into the blood. Aldosterone is an example of a mineralocorticoid, which retains water for you. It's made in the zona glomerulosa layer of the adrenal cortex. And you'll see that in your lab. The gonatocorticoids are made by the zona reticularis, and they are weak female sex hormones. So you never thought they're responsible for female sex drive, you know, minorly. You never thought the adrenal gland had anything involved with female sex drive. So now there's a tidbit for you to know. Gonatocorticoids, strange. Then glucocorticoids, you can know from the word, gluco means sugar. They're metabolic hormones. and they increase sugar availability in the body. So they also allow sugar to be available. They act in a way, I guess you could say, like, you know, glucagon, similar, synergistic a bit. So glucocorticoids, those are the adrenal cortex hormones. The adrenal medulla is completely different. Everyone make a fist and then put your hand over it. Your hand over it is the adrenal cortex. Your fist, move your fist, that's the adrenal medulla. It's covered. Now go like that. The adrenal medulla is like a knot of nervous tissue. It makes you punch. It makes you angry. It makes you, here's the word, fight or flight response. It gives out hormones known as epinephrine and norepinephrine, which increase your heart rate and your blood pressure and get you to do that fight or flight response. You know, you're angry, you know, Demplay gives you a test, you don't know what you're doing. You're like, you know, good Demplay, that's your adrenal medulla. That's your knot of nervous tissue that causes you that fight or flight response. And again, it increases your heart rate. This is a term you don't know yet, but I'm gonna throw it at you. The stroke volume, that is the amount of blood coming out of your heart. So your blood is supplied with more, your blood supplies your heart and your muscles more so that you have what we call that fight or flight response. Your sympathetic nervous system is activated to stimulate a reaction in your body a lot. Now, that's your sympathetic nervous system. Now, if you remember, you have a whole parasympathetic to relax you. And they work at, you know, to keep homeostasis. Let's talk about two different diseases of the adrenal glands, the Cushing syndrome and the Addison's disease. Cushing syndrome is known famously really as a hypersecretion of glucocorticoids, often due to an adrenal tumor. Cushing syndrome causes facial edema, maybe a buffalo hump. That means and you can Google on your own. I don't want to spend the time to do it, but you can Google some pictures on your own of Cushing's and Addison's to get an idea. But I would say it's very marked, the change when a person has Cushing's, where they have fat deposits, particularly the back of their, you know, the top lower part of their neck. There's more fractures, more muscle atrophy, fat buildup. It's a very marked. And Addison's is usually like a bronzing of the skin. You can Google it, look at pictures. Bronzing of the skin, there's hypotension, decreased sodium, increased potassium, and dehydration. A lot of weight loss. So hyposecretion versus hypersecretion of the adrenal glands, okay? The pancreas we've talked about at length already, so I'm gonna skim through this. Pancreas has two functions, all right? One is exocrine. It makes pancreatic juice to break down foodstuffs, and we'll talk about that when we do the digestive system. And it also is involved in secreting glucagon and insulin. In other words, sugar regulation. And the cells that produce insulin and glucagon, you have seen in your lab. They're islets of Langerhans, okay? And they're little islands. And I have you know, if you've gone through the lab yet this week, I have you know the difference between the pancreas, the adrenal gland, you know, the pituitary, how it looks under the microscope. And you have to know those pictures, because I have one picture on the practical. And I guess what I'm saying is those islets of Langerhans produce the insulin and glucagon, all right? Alpha cells happen to secrete glucagon, beta cells happen to secrete insulin, and the sugar level should be set at about 90 milligrams per milliliter. When sugar level is too high, insulin lowers it. When sugar level's too low, glucagon increases it. And to make a long story short, what are the symptoms of diabetes mellitus? Diabetes mellitus is the diabetes you know as inability to regulate sugar properly. And if you don't have enough insulin, okay, or it's not effective, these are the symptoms: polyuria, polydipsia, and polyphagia. Each one stands for a different word. Polyuria means more urination. Polydipsia means thirsty. Polyphagia means hungry. And why are you hungry and thirsty? Because the sugar is not, take a look at this picture. The sugar is not getting into the cell like it should in diabetes. Insulin is not effective in getting the sugar into the cell, so the individual is actually starving. The individual is actually not able to metabolize the fat like they should, and the sugar. So they break down fat, and we say it has ketones, ketone breath, which is a sweet type of breath when you're breaking down fat. And the diabetic can die due to a decreased pH in the blood. Why a decreased in pH? Because you're breaking down fats into acids and making the blood acidic. So it is a dangerous thing. And we have two types of diabetes. We talked about type 2. Type 2 we used to call adult onset. And that's because over the years there's down regulation, right? That the insulin and its receptors don't function right. That's type 2 diabetes. Type 1 diabetes is very different. That is when the pancreas itself is unable to produce insulin. That is, you're kind of born with it, or you get it at a young age, usually. Now, there are cases where it happens at an older age. It's an autoimmune attack, or an attack by your body on itself. That's an autoimmune attack. You can write that next to this word. Attack of your own immune system against itself. So autoimmune means your own immune system's attacking yourself. And it's an attack on the pancreas. We're not sure why it happens. We don't know. There's a hereditary basis, but we don't know. And it causes the individual not to produce sugar. Not to produce insulin, or certainly enough of it, and therefore sugar is not regulated properly. In the book, I address a very interesting, on page 556, the text box, the little chat box. I address the benefits of diabetes, that there may have been a benefit in that a person is able to forage longer for food if they're pre-diabetic and the sugar stays in their body longer, going back to the caveman time. So you might want to read that. It's interesting. It's in a text box because it's speculation. It's an interesting tidbit. And that's why I have these text boxes in yellow. Last but not least, the gonads. Notice I'm not getting into much on reproduction. That's because we have a whole system on reproduction at the end of the course. And what I want to say, though, is the testes and ovaries make each androgens and estrogens. I want to tell you that each of us make androgens and estrogens, whether male or female. I am male, and I make estrogen as well as androgen, or testosterone. We all have differing amounts, but men have more of the testosterone, and women have the more of the estrogen. But we both make both hormones. Again, those are the reproductive glands, and they produce that class of hormones. Last but not least, in the brain, there's a little gland known as the pineal gland. And the pineal gland, it's a cute little gland. It makes melatonin. Melatonin, and it's a picture. It's not a great picture, actually. 14.38. Figure 14.38. It's got a little picture where it would be. It's a little dot, and it makes melatonin. Melatonin makes you sleepy. The more melatonin you have, the sleepier you get. Okay, the more melatonin, the sleepier you get. And in figure 14.42, I have a picture, and it's a neat picture showing you how much sleep you need at different ages. Babies need a lot of sleep, and babies make a lot of melatonin. As you get older, things get smaller in the body. That's an old theme, all right? That's a theme of anatomy. As you get older, the pineal gland shrinks, making less melatonin. And I always tell you, if you remember anything about anatomy, anatomical structures, as you get older, generally, structures get smaller and shrivel away, except your car. Your car gets bigger. As I got older, my cars got bigger. I don't know why that is. You know, you always see the 90-year-old in a Cadillac. So anyway, my little joke for the day. I don't know how funny that is, but anyway, whatever. Last but not least, basically, I just want to say in darkness, more melatonin is produced. And that's why we think there's SAD, seasonal affect disorder, where in the darkness, people get depressed more and they sleep more. You sleep at night because your melatonin builds up as it gets darker. So that's an interesting point. I never forget a trip to Europe, to Germany, when I was about 25 years old. I could not sleep on that plane. And I always say, never take a drug from a stranger. I took melatonin from a person. I don't know why. And I was told, did it help me sleep on the plane? Absolutely not. I took a drug from a stranger. I was freaked out the whole time. How stupid. See, when you're young, you do crazy things. But anyway, I never forget that. And but they say, it helps your sleep patterns. a lot of you going into the health field, there's what we call a night shift. You don't just need someone in the day. And the night shift does disrupt sleep patterns. Studies don't show that melatonin helps those sleep patterns. And there's a lot of negative studies with poor sleep being related to weight gain, death, disease, you name it. So that's a challenge for the healthcare professional. The melatonin and the amount of sleep we need. On a positive note, you need a lot less sleep when you're older. And they say you should have a regular, if you're working the night shift, you just have to have a regular pattern of sleep. No TV on, no one bothering you. Keep it dark. You've got to keep your melatonin. You know, the pineal gland gets active when it's dark. So you got to keep your pineal gland active and keep it dark when you do the night shift. Very important. Okay. This is a concept map that I have on the overhead before you, and it has a circle around all of the different glands and their associated hormones underneath and the link between them, okay? As you can see, everything kind of links to the hypothalamus, but there are clearly links between other areas like TSH and the thyroid, and I have a little melatonin with someone sleeping right there. So when you do a concept map, it's very personal. It's how you want to do it. Like I have little definitions here to help me remember. I have, whoops, here, you know, with the pancreas, whoops, alpha and beta to help me remember. So when you do a concept map, you might want to do all cartoons. I don't grade a concept map, but I do want you to do a concept map for each book. So you get an idea, I mean, for each chapter. So you get an idea of what, how the terms are related to each other, how the concepts are related. You know, I don't assign homework. But, you know, if you wanted to do some questions, you could do question 9 and question 10 of the multiple choice questions. Okay, let me stop the recording so that we're able to